Welcome you all to the live session 11 of the course Manufacturing Process Technology, first and second. So here we will solve some of the problems based on the video lectures of the week 12. So let's get started with the first problem. So this is the first problem. Please first of all try it by yourself. After that we will discuss it together. Okay, let's start discussing. So in this problem it has been asked, in electron beam machining, as electron strikes the workpiece, and these are the options. So first option is their kinetic energy is converted into heat. Second is they get scattered. Third is mechanical erosion in the workpiece takes place. Electrochemical etching takes place. So let's try to understand how machining takes place in electron beam machining. So in electron beam machining, what we have a workpiece which we want to machine, and we have a beam of electrons. So, so all this complete setup is kept in a vacuum chamber. So this is totally vacuum. So here we have very high vacuum. So electrons are produced from the tungsten electrode, and they are accelerated towards the workpiece so that they could attain a very high velocity. So there is because first of all the electrons are emitted from as a thermionic emission, and then there are some electromagnetic lenses are there. they they help they help electrons to focus towards the workpiece, as well as some electric, because of the electric field, electrons they get accelerated towards the workpiece, and meanwhile what happens, they attain high kinetic energy. And when these electrons strike to the workpiece, they immediate immediately transfer all their kinetic energy. What so what will be reaching here? Electrons with high kinetic energy. Now when these high kinetic electrons they will strike to the workpiece, what will happen? They will transfer those kinetic energy to the workpiece material. But this energy is very high. So in very small area, large amount of energy, kinetic energy has been transferred by the electron, and therefore immediate temperature rise of localized temperature rise of workpiece material takes place, and because of the heat produced from the kinetic energy of the electrons, the workpiece material get melted, uh, and if sometimes energy is so high, the workpiece material direct gets evaporated. So in that way, in this way, material removal takes place in the case of electron beam machining. But here it is. Hi Praveen, do you like to answer this question by yourself first? If you want to try by yourself, you can give your answer in the chat box. And anyway, I am explaining the solution. So if you want to try, you can give your answer in the chat box.
Answer is option A.
Yes, yes, correct. Yes, correct. That's what I was also explaining. That in electron beam machining, basically electrons get produced at the here we have tungsten filament, and from there, because of thermionic emission, electrons get produced, and after that we have uh, electromagnetic fields through which the electrons get accelerated toward the workpiece, and finally they strike to the workpiece to a very localized region, and they transfer their all kinetic energy to the workpiece immediately, and material gets heated. High amount of heat is produced in very small region, because of which material gets melted or it gets vaporized, and that's how material removal takes place in the electron beam machining. But here uh, only only problem is that we cannot use it to for high material removal processes. It is used for to create some uh, complex shapes, which are very difficult to make with the other manufacturing processes, and this process is very high energy consuming process. So this process is used only for very specific purpose, where we need uh, where we need to go for some some intricated shapes, narrow shapes, which cannot be done by conventional method. So correct answer is A. Okay, so let's move to the next question. First of all, please try it by yourself. Then I will tell the answer.
Uh, Option B is the right answer. Drilling holes and cutting narrow slots.
Yes, yes. So in this problem, what has been asked? The electron beam machining is most appropriate for, and these are the options: machining flat surfaces, drilling holes and narrow slots, patterning large area in one steps, or all the above. So uh, actually, uh, correct option is B, because I already told that electron beam which is produced, suppose this is the electron beam, its diameter is very small. So it's near about uh, let's say 25 to 50 micron. So suppose if we have some flat surface, let's say by if you have, if you want to create some flat surface by electron beam machining, and which has dimension, let's say 200 by 200 and electron beam is very small, it is here point. And suppose if you want to create that kind of surface with electron beam machining, first of all, it will take a lot of time, even if you want to do that, as well as it is very costly because it consumes lots of energy. So this, although this process is not used for creating flat surfaces at all. And now coming to the drilling holes and cutting narrow slots. Yes, it is used for creating holes because suppose if we want very narrow holes, so suppose this is the workpiece, and if we want holes which is in micron range, let's say 50 microns. Praveen, can you mute because it is creating some disturbance?
Yes, hello.
Yeah, you can mute. Some noise is coming.
Okay, okay.
Yeah. So suppose if you want to create a hole of, let's say, 50 micron, in that case, what we will do, we will take the workpiece, and with the beam itself we can drill a through hole inside the material. So if hole size is very small, then directly we can use the electron beam, and by the method, by the uh, material gets melted as well as it get vaporized. So by, so hole gets created. So a small hole, if it is in micron range, then just by the beam of electron we can create holes. And that too, remember that if hole length is very high, then it is very deep, then it will not be straight, some tapering will takes place. So but if you want to create big hole, uh, if it is not in the order of the 50 micron, that can also be created. But in that case, the beam has to travel. Suppose we want to create a hole of 10, let's say, uh, 5 5 centimeter or 50 In that case, what will happen? This beam will travel. This beam will travel to the diameter of 50 and that's how this material gets removed. But again, creating this much big hole from the electron beam, it is not economical. Therefore, it is mostly used for creating narrower holes or narrower patterns or very narrow machinings. Here, it has been shown cutting narrow slots. Yes, if you want to create some very narrow slot or some microfluidic channel, in that case, this process is the best. But if you want to do some machining for the bigger slots, in that case, this process is not economical. So correct answer is this one. And this patterning large area in one step. So basically patterning process, it is mostly used in the as I am aware of, in the semiconductor industries, where we have a big wafer. Suppose this is the silicon wafer, and here we have to make some here we have to do some machining, some we have to create some pattern so that we could uh, we could make some shapes which is used for the electronics engineers. So this kind of pattern we cannot make by the electron beam machining in one go. So we have already studied the photo lithography, those processes are used to create pattern in the silicon wafers. So electron beam machining is not suitable, because if you want to make uh, any any specific geometry, then only beam can be present only at the one location. So we have to wait a lot, and in one go it is not possible. So these are wrong. Only correct option is B. So we will move to the next problem. Please read the problem and give the correct answer. After that, I will tell the solution. Yes, I have got response from the Nagasil Nimas. Praveen, do you want to give your answer?
Option A.
Okay. Okay, let's see what is the correct answer. So here I am showing a schematic of electron beam machining. Here we can see this is the location where electron gets produced. So basically here, that is called the cathode. You might be already aware of cathode rays. Yes, Praveen, you you
No,
have.
sorry.
Okay, okay. So as you already have studied in your earlier classes that uh, because of thermionic emissions, electrons can be produced from the cathode, and therefore they are also called cathode rays. So here we have a tungsten filament. The job of tungsten filament is to increase the temperature. So we are aware of tungsten filament can go more than 3400 degrees Celsius. That's how high temperature can be achieved using the tungsten filament. And we have a material which has a low work function, so that uh, when because of this thermal energy, electrons should get start emitting from the surface. So and after that we have a control grid which directs, which allows the electrons to move only towards to the bottom direction. And after that we had anode, and you can see there is a potential difference between this anode and this cathode. Because of this potential difference, whatever electrons is emitted from the surface of the cathode, because of thermionic emission, they are get accelerated. So those electrons get accelerated according to the field. So here it is towards the bottom direction. Now after that we have some filters diaphragm which allows which allows the electrons which are moving towards downward direction. And then we have focusing length, whose job is to focus at one point. And at the end we have a deflector coil. Basically deflector coil controls the where the beam should focus. So with the help of deflector coil, it adjusts the field in such a way so that if it is needed, we can move the beam to this location, we can move beam to this location. So let's come to the problem. In electron beam machining, the order in which electron beam pass after. So, so first one where we have seen it generates from the cathode, passes through the anode, and then to the focusing length, and at the end it comes to the deflector coil, which controls where it should fall. Yes, so correct answer is first one. Okay, so already you have given correct answer. So let's move to the next problem. Please read the problem and you can give your response in the chat box. Yes, Praveen?
Option D is the right answer.
Okay, yes. Yes, so both of you are correct. So here it has been asked the emission current in electron beam machining depends upon which of the following factors. So as in previous problem, I have shown that we have a tungsten filament which increases the temperature, and we have a cathode material, and cathode material has property. Cathode material, basically what it is, cathode material is just such kind of material which has low work function. So this is tungsten filament, this is cathode. So here we are giving a negative voltage, and after that we had anode. Okay, so you can see it is the same. So here it has been asked electron beam emission current. So electron will come out from the cathode material because of temperature rise. So and whatever, and it gets accelerated because of this potential difference. There is a field because of this potential difference between anode and cathode. Therefore electrons get accelerated, and how fast electron will move, that is going to decide the beam current. So beam current is nothing, it is a charge flowing per unit time, and it directly depends on the number of electrons. So yes, if cathode material, it depends on the cathode material, because cathode material, if work function is low, so cathode material, if work function is low, work function is low, then electrons will come out easily, and therefore by providing uh, less energy we can produce large number of electrons. So beam current will be higher if work function is low. And next is temperature. Yes, if temperature is high, then definitely more electrons will come out, and if more electrons will come out, then again beam current will be higher. And similarly the voltage of supply, if voltage of supply between here it is more, then electrons will accelerated faster, and if they will accelerated faster, then number of electrons passing per unit time will be higher, and ultimately beam current will be high. So therefore the correct answer is all of above. Okay, so already you both of you have given correct answer. So we will move to the next problem. Please, please read the problem and you can give your response in the chat box. Okay, Praveen has given his answer. Sorry, Naga Srinivas has given the answer. So Praveen, do you want to try? Okay. Yes. Yes, you both are correct. So basically, what has been asked in the problem in electron beam machining, the depth of penetration of the melting temperature is. Then we have when we have to fill in the blanks to the melting temperature of the workpiece. So in electron beam machining, what happens? This is the workpiece. Electron beam comes, and because of this beam, the material starts melting because of transfer of kinetic energy, which gets converted into the heat and which melts down the material below the beam. And this depth, how much this depth will be related to this the melting temperature. So that's what has been asked in the problem. So in the lecture already it has been sir has already proved by the dimensional analysis that there is a relation which looks something like this, where where we have p. P is nothing but beam power. So that is nothing but accelerating voltage into beam current. And d is the diameter of the beam. V is the velocity of the beam with respect to workpiece. Is the thermal conductivity of the workpiece. And rho, this multiplication of rho c, it is the volume specific heat of the material. Material or the workpiece material. And theta m is the melting point or the melting temperature. So rho c basically it is the multiplication of density and the specific heat. So rho is the density of the material and c is the specific heat, and their multiplication is called volume specific heat of the material. So definitely if the melting temperature of the workpiece is smaller, then we will get higher depth, basically more. By giving the same amount of energy, we can melt the more material. So and this relation actually it has been proved by the Buckingham pi theorem, as well as this it involves some practical knowledge also. So yes, this has been found to be working till date. So from this relation we can see there is an inverse relationship between them, z and theta m. So the correct answer is inversely proportional. Okay, so let's move to the next problem. Yes, so this problem is about the laser beam machining. So please first of all try it by yourself, then we will discuss it together. Okay, I got response from the Nagasrinivas. Okay, okay, so let us see it together. Okay, so the laser beam machining process can be carried out when the media for energy transfer between tool and the workpiece is. So these are the options. So first of all, uh, I will quickly write down the what is the laser machining. So laser machining is nothing. It is a laser machining is a technology that utilizes laser, or that uses a laser beam. What is the laser beam? Laser beam is nothing. It is a narrow beam of intense monochromatic light. So this light is used to cut different shapes. Shapes or profile or pattern for any kind of material. There is no limitation that material should be conductive or it should be metals. So nothing like that. So it can work for any material. And what is the full form of the laser? So it is the light amplification by stimulated emission of radiation. So this is actually very special light. It is not an ordinary light, as it has been already, the word light is coming. Okay, so what happens here? We have intense monochromatic light. How it is generated, we will discuss this. We will discuss in briefly. In brief, we will discuss. So somehow, suppose we are creating intense beam of light, and it is falling on the workpiece surface, and it is getting absorbed in the workpiece, and this light energy, because of this light energy, what is there inside the light energy? There is photons. And photons, what they have, they carry energy, and this energy is used to increase the temperature of the workpiece. Earlier in the ion beam machining, in electron beam machining, we have seen the electrons are coming and they were transferring the kinetic energy to the workpiece material. And here at the place of electrons, photons are coming and they are transferring the energy, thermal energy to the workpiece, and because of which the temperature of workpiece material gets increased. So it is very high. The temperature becomes very high where material can melt, it can, as well as it gets vaporized, as well as sometimes it gets ablated also. So this kind of machining, this is the process of which material gets removed, and this is called the laser beam machining. So here light is involved, photon is involved, and the question is all about the medium between the workpiece and the when the media for energy transfer between tool and the workpiece. Suppose we have laser beam head over here, okay, and we have the workpiece which we want to machine, and now in between there will be some medium, okay. So the question is all about what are the possibilities of the medium, whether it is air, liquid, vacuum, or any of them. So uh, for machining to happen, whatever photons are coming from here, it should reach to the workpiece. So here photons are emerging. So what do you think? What kind of medium is needed to so that photon could come uh, from the tool to the workpiece? Actually, photons can travel without medium also. They don't require any medium. So they can travel in the air as well as it can travel into the liquid. And if there is no medium, then also it can travel. You have seen the sunlight coming from the space where there is no medium. It is reaching to the earth. So they are nothing. They are just the photons. So basically you have seen the light can travel through the air as well as the water as well as the vacuum also. So the main thing is whatever photons are getting emitted from the tool nozzle, it should reach to the workpiece, and it doesn't depend upon the uh, air or the liquid. Yes, their speed will depend the speed because we know that the based on the refractive index of the material, the velocity of light changes, but it is not like it will not it will it will just speed will slow down, but ultimately it will reach to the workpiece only. So whether it is air or it may be some liquid or it may be the vacuum. So as long as photons which are emitted from the source, it is reaching to the workpiece, the material removal will takes place. So the correct answer is any of the above. Okay, any doubt? Clear? Shall I move with the next problem? Okay, since there is no doubt, so we will move with the next problem. Please read the problem and you can answer. You can give your answer in the chat box. Yes, I have got response from the Praveen. Okay. Yes, you both are correct. So, which are the properties of the laser? So, let's quickly, I will quickly tell you how basically laser is produced and how we are getting this kind of properties. And actually, this kind of properties is required for the intense energy. So, so what happens? We have some actually laser can be produced with the help of some specific materials. So like CO2, ruby. So there are some specific class of materials through which there is possibility of producing laser. And what happens, how it is produced. So I will quickly show it to you just by a simple case. So suppose here I am showing the energy level. So there are basically, if we in all materials, uh, in normal case, if we are not providing any kind of energy which is going to excite the energy level of the electrons, so normally it, its tendency is to for the electrons to remain in the ground state. Okay, so this is nothing but the ground state. And here it is the some, here we have energy level 1, and in between we have some uh, let's say EM or some metastable energy state. So this is the case when we are not providing any energy to a material. So most of the electrons will stay on the in the ground state. So whatever the number in the ground state, let's call it with n. And suppose we are providing some energy, and that energy is exactly same as the this difference, that the from the ground level and energy level, let's say 1 excited state of 1. If we are providing energy which is equal to this, then what will happen? Then this, if suppose we are providing that energy to the this electron, it will go to the excited state E1. Okay, so it will, this is the property of the material, that electron can absorb only some specific quantum of the energy. So it, if we give higher energy, then also it will not absorb. If it will we will give lower energy, then also it will not absorb. So if we give exact amount of the difference of this energy level, then only electron will jump from ground state to the excited state. And this process happens very quickly. So let's see laser. Okay, laser is what? Light amplification. Light amplification by stimulated emission of radiation. Stimulated emission radiation. So what we want here, we want a light beam which should get amplified. We know light has properties of both particle as well as the wave. So now let's talk about the wave nature of the light. Suppose we have one beam of light, then it will have some energy. Now suppose if we superimpose another wave over it, what will happen? Its amplitude will increase. Okay, so that's what we want. We want to increase the light energy of the light beam so that it would be sufficient for rise the temperature of the workpiece material, and that's how the machining will takes place. Therefore light amplification is very important. So now how how it is happening, I told. First of all, we had some lasing material which has property that we have excited state, and in between we have some metastable state. For simplicity, I am taking one metastable state. So first of all, what I told, from external, from first of all I provided some photons, some light. Okay, some light I have provided, and light means what? I provided some photons which has energy equal to the gap of the difference, and when it gets it get absorbed by the electrons on the ground state, and now it the electron on the ground state is to the excited state. After that, suppose this happens to this also, it will also reach there. So this process happens very fast. So now after reaching the excited state, it is not like it will stay here forever. It will come down. But suppose if we are not doing anything, we are not disturbing this, then after some time these electrons, they will they can come to here, or they can come to the ground state also. So suppose it comes here, and after some time it will come here. So we know, in order to bring the electrons to excited state, it absorbs one photon. Then opposite will happen. When it will come down, it will also emit some photon. So here, suppose if it comes from here to here, then also it will emit some different photon, which is equivalent to the energy gap of this. And when it falls down to the ground state, again it will emit some other photon, which has energy difference of this. So this is the general process which will take place. If we not do anything, after some time the electrons will automatically come down to the ground state. Okay, but this kind of whatever photons will come by by themselves, if we not do anything, in that case the light which will come, or the photons which will come out, they will not coherent, they will not be in the same phase, as well as this is as well as it is not possible them to amplify, because they are not in the same phase. Because if you want to something to amplify, First thing is they should be in the same phase, then only they will superlap, then only we can superimpose them. If they are not in same phase, they are in some random phase, then no one can guarantee it will amplify. So what 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 is there? So something called stimulated emission. So the process which I told, which will happen naturally if we will not do anything, that is called the spontaneous emission. If we not do anything, after some time the electron will come to the ground state by emitting some photon. That is called the spontaneous emission. But now we want to control it. We want whatever photons will come out, they should be in the same phase. Then only we will able to use it for the amplification purpose. So there is something called stimulated emission. So yes, physicists have find out. Suppose if we have some photons here. Actually, I have drawn this metastable because in this energy level, normally the electrons stay for the 10 to the power minus s seconds. So it is very small. Whereas the in metastate stable, they can stay up to the 10 to the power minus 3 seconds. So here they can stay for the longer. So if they can stay longer, then there is a possibility that we can gather some more number of electrons here. Suppose earlier I told the number of electron in the ground state was n, and the number of electrons in the excited state it was n1, and suppose the number of electron which we are calling in the metastable state by ne. So we want accumulate the more number of electrons in the metastable state, so that in one go when we want these all these electrons together come down, and by doing this what will happen, the photons which will come out, they will be in the same phase or they are the coherent, and that can be used for the amplification purpose. So as was talking about the stimulated emission is nothing but this is the phenomena when we supply a photon of same energy gap to the excited state of electrons. Okay, so this electron is in the metastable state. If the photon of this energy gap comes and hits to the excited state electrons, then it will come down to the ground state, as well as two photons which already which comes and hit to the this electron, as well as one additional photon of same energy. So basically two photons will come out, and this process is called stimulated emission. Basically this electron gets stimulated by this photon to come to the ground state and release an additional photon of same energy. So that is called the stimulated emission. So with the help of stimulated emission, we make sure that all the photons which are collected in the metastable state, they should fall down together. So that they all should be in the same phase. So this complete setup is kept between the two mirrors. So Initially, we have some CO2 atoms. I will show it by another. I'm taking example of CO2 because it is very common. So we have CO2 atoms, and we excite them to go to the higher energy state, and then again we stimulate the high energy state electrons to come to the ground state so that photons come out. So photons are coming out as well as they are in all are in the same phase. And here we have reflectors. It is partial reflector, and this is com- complete reflector. So by doing this, what is happening? As time is passing, the number of photons in the same phase are increasing. If the number of photons in the same phase are increasing, it means the amplitude, light amplitude is increasing. Okay, and I told this mirror is partial. So partial means it has property after certain intensity of light, it will allow, it will not reflect. Basically, here it is the light wave is resonating. It is resonating as well as it is amplifying. But after certain amplification, this partial reflector will not allow to, is not able to reflect further. Then it will act as a transparent. Then after reaching that that amplitude of the light, it will allow to laser lights to come out. And this light which is coming out, this is the laser. And once the light came out, the process will keep on repeating again. Some some photon will come out, and as time passes, superimpose will take place and amplification will take place. And again, when the amplitude of photons will become such that amplitude of light has become such that this partial reflector will not able to reflect more, then again it will allow, after some time next beam will come. Okay, so that's how the laser is generated, and this is nothing but this is coherent. They all, basically whatever the waves are there, they are coherent, and they are monochromatic means only one wavelength, only one wavelength of light is there, and that wavelength correspond to energy difference between this metastable state and ground state. So wavelength corresponding to this region, only these lights are there. Okay, so that's why monochromatic word is used. So they are coherent, they are monochromatic, they are highly collimated. Collimated means they are parallel. Whatever beam coming out from the, this is called a cavity. Whatever, this is called cavity. So laser, whatever light coming out from the laser cavity, they are parallel. And that's why you see that even for the many kilometers, the laser beam not get diverged at all, because they are highly collimated. And therefore it is used for the machining, because it can provide concentrated energy to a very localized region. Therefore it is used for the machining of the workpiece. Yes, all you already told, the option D is correct. So let's move to the next problem. Please read the problem and you can tell your response in the chat box. Praveen, you can also give. Okay, yes, both of you have given correct answer. Yes, so based on the energy, energy density, the manufacturing processes, the they have been divided into different uh, zones. So I will quickly draw the same diagram. Here we have power density, and here we have spot diameter. So here these are in the micrometers: 10 to the power 1, 10 to the power 2, 10 to the power 3, or 1 mm, 10 to the power 4, 10 to the power 5, like that. And on y-axis, power is shown: 10 to the power 0, 1, 10 to the power 7, 10 to the power 8, something like that. And the power density is the watt in watt per mm square. So I will draw some regions. So this region is used for the electro discharge machining process. So you can see it is at the higher side. So electro discharge machining has highest power density till date what has been known to us. So after that something this comes. This is the region of the laser beam machining. So this is the working region of the laser beam machining. And there is a broad spectrum of electron beam machining. So this broader area, this is electron beam machining. And there is some smaller range. This is the welding arc where we have seen the plasma arc welding. So and on at the least power density side, what we have, gas welding or oxyacetylene welding. So what we can see from this diagram, we have categorized the different power source based on their power density as well as the spot diameter which is possible. So for the gas welding, we can see we cannot get smaller spot of diameter. So it is more than 1 mm. So gas welding cannot be used for cutting very intricate or very narrower shapes. So similarly, if we see the arc welding, it also has limitations. Here also we cannot able to uh, get the spot diameter of the 1 mm. So that is its limitation, as well as the power density which we can see, uh, that is also lower for the electron for the s- arc welding as well as the gas welding. So, but if you see these non-conventional techniques like laser beam machining, electrodischarge machining, here we are having flexibility to get very small spot diameter as well as very high density. Therefore, therefore these techniques can be used for machining those materials which are very difficult, which are very hard to do by the other methods. But again, here they also have limitations that we cannot get bigger spot diameter for the laser beam machining as well as the electro discharge machining. So based on the application, what kind of specific application we are looking for, and we use suitable process. So based on their power density and spot size, based on our requirement, we can use this diagram to, and we can choose what is the suitable process. Okay, and if we see the laser beam machining, it is coming mostly the higher power side, so that's why it is called, it is comes under the high power category. So already you have told the correct answer, so let's move to the next one. Let's read the problem. So please read the problem, and you can give the correct answer in the chat box. Yes, you both are correct. So basically, uh, if we talk about the ledger, so in general, this range of 0.1 to 70 microns of the wavelength, this means this this wavelength of light can be used for producing the laser, but here we are talking specifically all about the machining. So for machining, uh, we only very specific or narrower ranges available which can be used for the machining purpose for the laser, and that has been found out, this one 0.4 to 0.6 micron, because for the laser beam machining two things are there. One, it should have sufficient power so that it could able to it could able to rise the temperature of the material sufficiently so that melting or the ablation or the vaporization takes place, and same time it should get absorbed by the material. So all the materials cannot all the frequency of or the all wavelength of the light cannot be absorbed by the material. So this is the practically found that in this range satisfied the both conditions where it has sufficient power to remove the material as well as it gets absorbed by the material. So yes, it is memory based answer. So the correct answer is 0.4 to 0.6 microns. So nothing more here. So let's move to the next problem. Please read the problem and you can keep response in the chat box. Kalikapuram, Rajesh, can you explain CMOX and PESY methods? Actually, I am here. We are discussing about the manufacturing process and which comes under, and these are the out of syllabus. So these are mostly for the, I think, electronics people. Hello, yes, Kalikapuram. So the methods which you are asking about, so it has been not taught in the lecture. So I think this is out of scope. So this this is all. Here we are discussing about the video lectures of the week 12, where we have been taught about the manufacturing processes like laser beam machining, uh, electron beam machining, as well as some additive manufacturing processes. So is it the question which you are talking about, is it lies in this domain?
Sir, it is in the assignment 12, sir, and it is in the additive manufacturing process. Some ion, one video it is there, sir, but it's not clearly explained, sir. It is in the 12th module only, 12th week only, but it is not clearly explained, sir. In third video, I think additive manufacturing video, it is available, sir. They are simply just briefly, sir, explained. So the question is also there in assignments regarding this silicon on layer methods.
Okay, so okay, is it related to additive manufacturing, and this is used for developing the silicon chips, is it?
Sir, silicon on layer, sir. Yes, silicon on layer. It is in the video, sir, but it is only 2 minutes video.
Okay,
Simply briefly I can explain. So if possible, you can explain something more, sir, if
so
possible.
I can, yes, I can tell you like what happens in the, okay, here I will show and then I will probably I will remove it, then I will come to the problem 10. So uh, in semiconductor industry, our aim is to develop different uh, transistors or diodes in very small size. That's how miniaturization is happening. So but how they are made, so it is not like so if you see a microprocessor which is probably 1 inch by 1 inch, so if you see this kind of microprocessor, it has millions of transistors. Okay, so but how they are made, it is it has more than the 100 layers. Different processes has been done in order to control the composition as well as the doping. Doping has been done in very controlled way. So this there we get very small size, in less than micron size of transistor size. But how they are made, the thing is, if you see the silicon wafer, it is nearly about 8 inches to 12 inches. The initially it is this much bigger, but from this silicon wafer we are creating millions of pattern in this silicon wafer, and we are producing some microelectronic device. It may be chip, it may be SSD, it may be processor, but every the process is the fundamental process which is involved. If we want to generate very small controlled pattern or some controlled environment where we have controlled composition of electrons and the holes, then we have to control the doping process. So doping process is nothing. I would just take example. We have some silicon wafer, and we want to create some oxide, silicon oxide layer, but it should not be uniform. It should be so. These are very smaller size. If you see this, it it, it should be like 0.1 micron, or let's say 0.01 micron, in this range. So we have silicon over which we want to create some, let's say, silicon oxide. So if you just simply think, we have silicon wafer and we want to create silicon oxide, what we are doing ultimately, somehow we are bringing some oxygen and we are implanting in these very specific regions. Okay, so there are methods like some dry methods, some wet methods are there, through which we are just able to supply the oxygen over the silicon wafer. But in order to make them very location specific, what we used photolithography technique. From the photolithography technique, you must have remembered that we can achieve the capability to what region of the substrate will remain masked and what region of substrate will remain uncovered. So if this region has to be reacted, then definitely other regions have to be masked. Other regions have to be masked. And if these regions are masked and we are supplying oxygen atoms, we are creating some oxygen environment. Then this oxygen is going to react with the nascent silicon wafer, this surface, and this will keep on diffusing inside the silicon wafer. But how much depth it will go, it will depend on the concentration of the oxygen. Here, what is the concentration we are creating over here, as well as how long we are exposing this surface to the oxygen atmosphere, also to the temperature, also to the surface finish of this surface. So these things are practical things which are going to decide up to what depth this oxygen will go and what should be its concentration of this silicon oxide. So this is how it is done. But how this photoresist, uh, how this uh, how this layer, which is masking layer, has been created, that has been done by the photolithography technique. And you already have uh, you are aware of the negative photoresist as well as positive photoresist. So that is those things comes into the picture in order to masking this surface. Once doping gets over, we we use some chemical to remove this masking layer, and ultimately we will left with the desired pattern of the silicon and silicon oxide. So this is the very common process for all the semiconductor industry. So this is what I am aware of. If it is you are asking about something else, then probably I have to read it more. But this is what I know for the silicon industry, how doping is done. And this I have told only about the one layer. Similarly, thousands of layer has to be done in order to make a good processor, and that's why it takes more than more than 1 month of time for single wafer. It has to go to the different fab labs, the labs where this process is done, that is called the fab. So this has to go to the different platforms, and it takes more than months to create to complete the all the process for getting a good semiconductor which is used for the transistor purpose or processor or SSD device. So this is what I know for the micro manufacturing related to the semiconductor industry. So probably you can read more, but this is what I know and this is what I have explained for your knowledge. So let's come to this problem. Which of the following is true for the fused deposition modeling? Yes, please. Uh, I think
So thank you,
everybody.
sir.
Okay, thank you so much.
Thank you.
So, okay. Yes, already all of you have, I think, given the answer. That's it is an additive manufacturing process. So, yes, till now we have seen the all kind of processes where we were interested to manufacture the products by removing the material. So either it was conventional machining process, either it was non-conventional machining techniques like ultrasonic machining or abrasive jet machining or ADM, ECM. Those things we have studied. And later on we have studied about the electron beam machining, ion beam machining, and laser machining. So till now, in order to get the final product, we were studying the uh, manufacturing techniques where material removal was involved. So in last few years already you are aware that 3D printing, which is called additive manufacturing, simply it is called the 3D printing, or it is also called regenerative process. Here the any component is made by the depositing layer over layer. So here it has been shown. Here just a simple process has been taken. Uh, Usually we have a spool. There is a polymer which is called ABS. So polymer which is ABS, acrylonitrile butadiene. So this is the common polymer which is used for the 3D printing process. So it has a spool. So ABS has been stored in, so it the, so in the spool ABS wires are stored like that, and these wires are fed into the nozzle of the 3D printing machine, where two things are happening. One is this wire is being pulled. This wiring is being pulled. Also here some heat has been supplying. So this heat is just melting the material over here, and it is making sure that the material is heating and it is making it soft so that it could be able to deposit in programmed manner. So if you see here, it is very simple shape where where this is the first layer, and over which we have second layer, third layer, fourth layer. Likewise material is getting deposited. So initially what we have some CAD model, and this CAD model, this here actually .stl format is used. It is called stereolithographic format. So it is nothing, it divides the CAD into small triangles. So basically .stl format contains information of the whole 3D model in the form of triangle surfaces. So this has been given to the machine, and what machine does, it brings out the coordinates of different triangles. So there are many triangles. So there is something called slicing algorithm. So it slices the whole 3D model into different layers, and those layers or get deposited one over each other by this 3D printer, and that has been controlled by the CNC codes. So this kind of process is called the fuse deposition modeling. So this is the very common and very basic 3D printing process, which can be seen almost in uh, everywhere in all labs. I think it will be there. So the correct answer is it's an additive manufacturing process, but still there are lots of issue in the additive manufacturing process. The components which are made by the additive manufacturing process, still they are not completely finished. They, because of this layer differences, there are something called staircase effects are there. Yes, Praveen.
Hello,
Yes.
sir. I have
Yes.
a 3 4 question at previous assignment. Some question answer doubt.
Okay.
So, so will you please solve that question answer?
Yes, definitely.
Uh, because last session I already talked with Balaji, and Balaji was there on that time on last lecture.
Okay.
Previous problem solving. They told me to send mail to some 41242001 @nitt.edu.
Okay.
Already I have sent four
Okay.
days already over, but nobody gave some reply.
Okay. Okay.
So
So
my first
yes.
question is from week assignment week 11.
Okay.
Assignment week 11. Question number first.
Okay.
Question of
So
first is dash is the dash proportional to dash in ECM.
okay. Yes.
But here answer was given option B, volume removal rate directly proportional density of the anode. This was the given the answer.
Okay.
But I know the volume removal rate is atomic weight into current divided by valency into density into Faraday.
Yes.
Means here the volume removal rate is inversely proportional to density.
Yes.
But in our
Correct.
option,
Yes.
but
Yes.
in our option, volume removal rate is directly proportional to density of the anode. So it will not a right answer, na?
Okay. So the answer was given that that is
I
right.
think answer should be A.
Wait, let me open that same assignment. Okay.
Yeah, please, please.
Yeah. I think I also have solved similar kind of question in my previous lecture. I will also check that. Okay.
But till now, option is showing only option B is showing in
Yeah,
app.
if because it has some error, then definitely you will get marks for that. Don't worry for that. We will rectify it.
Because already 1 week over now. So how I know that was corrected or not?
Okay, so
Not
here
even got
against.
any email from that NPTEL site.
Okay, here, and I will open the solution also. So it was all about the ECM process. Okay,
Yeah, ECM process.
okay. So let me open the ECM process.
Week 11. Okay,
So
okay.
now you can see, is it
Uh,
visible?
no, next. No, next.
No, actually, I am talking about this formula actually.
Yeah, yeah, yeah. Okay, okay. Now,
Yes,
okay, let's see. Q equal to AI by rho ZF. Okay.
correct.
This is the volume revolve rate, na? Means here the density is inversely proportional, na?
Yes, definitely,
But
and
here
it
option,
is it
but in option it is showing directly proportional.
okay. So it's second option you are talking about,
Yeah,
volume
yeah.
removal
Second
rate
option is wrong.
directly the density of the anode. Okay, okay, okay. Yes,
I think first
yes,
option will
sir.
be the right.
Correct, correct, correct. You are telling correct. Density of the anode should be directly to the current. Yes, definitely that is right. There is no doubt.
Yeah. But here it is showing
Yes,
option
yes,
B.
yes, yes. We will bring attention to the respective team, and they will modify it. Okay.
Okay, next
Yeah.
question, please. Same assignment.
Yes.
Question number 9.
Question number
In
nine.
the yeah, thermal machining process,
Okay.
heat source is used to remove material from workpiece R. All of the all option they have given means options. If option actually is light, plasma, and electric discharge.
Yes.
But actually, heat source is the plasma, electron, ions, and photons are the main heat source in thermal machining, na?
No, actually, all of them are there. Correct. Like if you talk about the let's say laser machining, so here material is being removed because of the thermal energy which is being produced by the photons. Okay.
Okay.
So in laser machining, if you see, the light is being or the beam of light is used for increasing the temperature of the workpiece material locally, so that the material could start melting, vaporized, as well as it sometimes it
Electric.
go for the ablation also. So heat is being produced because of the light. So that is correct. And coming to the plasma, yes, it is well known. Uh, like you have seen that cutting plasma or cutting or oxyacetylene flames cutting there, also plasma is there. So yes, plasma is correct. And in electrode discharge machining, uh, the material is getting removed because of the uh, discharge is taking place, and discharge is nothing but spark where material locally gets melted, and because of the shock waves it gets removed. So yes, here in electrode discharge machining, in very small area the material gets melted, but because of the shock waves there is negative creation of negative pressure zone, and the material gets removed because of the shock waves. So here also the fundamentally the temperature rise has been taking place very localized region, material is melting. That's why the correct answer is all the above.
Okay. Then week 7.
Week 7, wait. Yes, metal forming.
Metal forming, week 7, question number 10. Assignment question number 10.
Question number 10.
Yeah.
Okay. Yes.
Yeah, here the actually true extent,
Okay.
if you stretch material from length L1 to L2,
Okay.
then the true extent should be minus ln of L1 by L2. Already this is question, Bhattacharya sir already solved that question in
Yes,
the
yes.
lecture before.
Okay.
But here option is showing, C option in app, it is showing the right answer.
Minus L2 by L1.
Yeah,
Okay.
and yeah, minus L2 by L1 is, it is showing in app.
Okay.
But I think option A and B both are correct.
Yes, they are same
ln L,
only.
yeah, yeah,
Yeah, they are
and
same
also,
only.
yeah, true extent also already they have solved 2 3 question in video. Same
Yes,
formula they
yes.
have used.
Okay, okay. Okay, so here I think some mistake is there. Okay.
Yeah, please note down this question also.
Okay. Okay. Question number 10 in assignment 7, and
7,
question
yeah,
number uh
1 in
1
assignment
assignment
11.
11. Okay. Okay,
Next,
okay.
one more question.
Yes.
Question number in
Hello, your voice is not coming to me. Hello. Yes.
week 6, question number 9.
Week 6, question number 9.
9. Yeah.
Wait.
Yeah, I think this question should be bonus because data was wrong.
Okay.
If you check with that data, then the answer should be 1 V equal to 121 minus 16L.
Okay, but I
That
think
is,
you might have received some email regarding this question.
yeah, yeah, yeah. Mail?
Yes.
No, I didn't got any mail.
Okay. Okay, so okay, so let me note it down all at one place.
Yeah, yeah.
We will check, and I will give my email to you, and I definitely respond to you. Okay. So the question number 9, problem assignment number
6. Because in here,
assignment
current and
6.
arc length should be inversely. Na? If current is high, then arc length should be the minimum, low.
Okay, the direct link and the linear. Okay, characteristics. It has been very similar kind of problem I have solved. Okay, okay, I will get back to you. Okay, whether the solution is correct or not, I will tell you. Okay,
Yeah, yeah,
and
yeah,
if it is
please.
wrong,
Please
then you will get the bonus mark for it. Don't worry for that. Okay,
look into this. And
question.
one more question, last question.
Yeah, let me note down
Yes,
question number 9, assignment 6, question number 1 in
6,
assignment 10, 11,
11. Question
assignment
number 10 in assignment 7.
assignment 11, question number 10 in assignment 7.
Yeah. Then last question
Okay,
in assignment 5.
okay,
Question number 3.
question number 3.
Here actual में 5 plus lambda minus alpha by 2 equal to pi by 4.
Wait. Assignment 5, let me open it. It is
Yeah.
from the metal cutting. Question number
3.
3. Okay, yes.
It is actually this relation is given by the stabler. Already sir already given in video they have noted down that equation they have written and they told stabler equation they have given this equation. So I don't know how this question Sheffer equation is wrong. Sheffer equation means alpha, alpha by 2 equal to pi by 2 is the Sheffer equation, no?
Wait. I can clear this immediately.
Yeah, please check.
Okay. This is for the week number
What
5.
is showing in
Week. So 5 plus lambda minus alpha, that is Liam Schaeffer.
alpha by 2?
Yeah.
This is the question.
Yes, that is Stabler relationship. 5
Yeah.
plus lambda minus alpha by 2 equals to pi by 4. This is the Stabler's relation. Yes, correct.
Yeah, established. But option is given C, Sheffer.
No. It should be pi. For the Schaeffer's, the Schaeffer's relationship is the 5 plus lambda minus alpha is equal to pi by 4.
Yes. Yes.
Okay.
So please note down this one. Also, this should be corrected.
Okay, wait. I will note this also. Question number 3. Assignment 5.
5. Because this question I got a mail regarding they told this should be a question bonus question. But I think question is right now. As option is also given a right answer. Option is given. Then why they are giving a bonus?
Yes, definitely. Because everything is right, so they need to change the answer.
Yes.
Okay.
Yeah.
I will inform the team and
Yeah. So
they will
total
give
4 questions you have noted down, na?
Yes, assignment 6, question number 9, assignment 11, question number 1, assignment 7, question number 10, assignment 5, question number 3. Okay?
Yeah. Total 4 questions. Yes.
Okay. So I will for assignment 5, question number 3, it is clear that the answer given is wrong, as well as the assignment 11, question number 1, that is also
Yeah.
given wrong. So now
And assignment 7 question number 10 is true extent.
true stem. Okay, yes. So
Simple formula, na? This is simple formula.
Yes, simple formula only. So that is also given wrong. So problem number 9, I will solve it by myself, and then again I will come back to
Yeah.
you. If it is wrong, then I will inform the team. Okay.
Yeah. You please because the second solution you have in solution you have given first option first option came a plus 8.5 b equal to minus 15. That is the right. Okay, first equation.
Okay.
But second equation is a plus 6b equal to different value.
Okay.
Yeah, this is when you apply the length equal to 6 mm and current equal to 480 ampere, then the equation will be different.
Okay. I think for this problem, already some email has been circulated. Okay. I will see and I will let
I
you know.
also
Okay.
given mail.
Yes. I will let you know. Okay. And I will write down my email, and regarding all these 4 things, you can get reply from me. Okay.
Okay. Because
And
last session Balaji told me you sent all question with a solution to mail. Already I replied. They told within 1 day I will reply you. But till now
okay.
no reply came.
Okay, so he will reply, but I will also reply. Okay, don't worry for that.
Yeah, yeah,
We will
yeah.
provide
Because
complete solution to you.
next, yeah, because after 10 days exam will be there, na. So if
Yes, yes,
question is
yes,
right, then I will understand, na.
yes, 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 yes. Okay, definitely we'll do that. Okay, and next, I think one more session is there from my side also. So 25th will be last session for me. So
25th.
yes, okay,
Okay, sir. Okay.
okay. So regarding these four things, rep- I will reply. You can ask me in the email also. I have written down the email,
Okay, please
and
tell me your email.
you, yeah, you can note it down. That is in the chat box.
Okay, in chat box, you please give me.
Yeah, I have already typed.
Okay, 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 okay.
Yes. Okay, and in the last session 25th, you can also join, and I can update you again here.
Okay.
Okay.
And also, sir, please try to update in app also, sir.
Okay. 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 So
Oh,
if any changes, if anything is going to the bonus or any modifications, that definitely you will get notified in the Google groups or as well as on the email also.
yeah, yeah. Okay, sir.
Okay.
Okay.
Okay. Okay. So now let's come back to the problem. I think yes, we have done with the problem number 10. So let's come to the problem number 11. Yes, you can give your response in the chat box. After that, we will discuss it together. Yes, yes. So uh, here it has been asked about the stereolithography. It is also one kind of manufacturing process, uh, additive manufacturing process. So here I have shown that just a diagram. Basically, here again we are manufacturing the component layer by layer, but here we are not depositing like in the fuse deposition modeling. We were melting the material and we were depositing layer over layer, but here it is not like that. So it is here we have some polymeric material over here which has property it will react with the lasers or this light. Okay, there are some photochemical reaction takes place, and because of which this polymer gets solidified or it gets settled. But here uh, uh, we do this thing layer by layer. So suppose we want to make a component something like this. So initially we will have sorry initially we will have the polymer like this, and this is the platform over which we are manufacturing, over which we are depositing the material. So we will bring the platform just the depth, we will bring to same depth as this first, similar to the depth height of the first layer. We will bring the platform exactly same depth, and then with the help of laser beam it will travel from here to here, and material gets deposited over the platform, and then again we will bring down the platform a little bit more downwards, and again we deposit another layer. So likewise we keep on moving the platform downwards, and we are using the laser beam. We are programmed in such a way so that it should it it should react only the photo. It will react with the polymer in desired region in order to get the desired shapes. So this triangle will be formed something like this, layer by layer. And this effect which you are seeing, something looking like stairs, that is called the staircase effect. That is the biggest one of the biggest problem of the 3D printing till date, and people are trying to minimize this effect so that it should become straight line. Staircase effect. Apart from then, many other problems are there, but this is the one of the major issue. So correct answer for this problem is the UV laser. UV laser is basically it is reacting with the resin, and it is uh, it is making it harder so that we could get the component. Yes, you are correct. And now let's come to the last problem of the day. Yes, you can try it by yourself first, then I will discuss it with you. Yes, yes. So both of you are correct. So it is a simple process only. So selective laser sintering, it is also a kind of additive manufacturing process. So first of all, we see in the fused deposition model where uh, we were first melting the material and we were depositing it one over another. Now after that we have seen the stereolithography where a beam of laser was coming, and uh, it was solidifying or curing the material locally for a layer by layer, and that's how we were getting the 3D component. Now let's come to the one more process. This is called the selective laser sintering. Here basically uh, again the component is made by layer only, but here the comp- the raw material is in the powdered form, and this powder basically, this is the cartridge of the powder, and this has its height has been controlled by this piston, and there is a roller which its job is to take the layer of powder to here powder bed, and it the powder get deposited throughout this powder bed, and this this is the power source. It may be it, it can be laser also. So the power source is there which comes in the selected area, and only in this region powder gets solidified or sintered. So here also sintering is being taken place layer by layer. So if you see this component, so it has been formed by depositing different layer of powder and followed by sintering. So this is also a kind of additive manufacturing process, and here continuous layer of powder, it is being sintered by in selected zones, and that's how the component is being made. So correct answer is B. So this is all for the today's session, and next session we will meet again, and uh, I will collect some some good problems from all the weeks, and that might be useful for your final examination. So yes, we will meet next week at the same timing with some problem, some most uh, most probable problems which can come to your exams. Okay, so yes, show all a good night, and we will meet in the next week. Okay, thank you. Okay, we will end the session here. Okay, good night. Welcome you all.